Hi everyone, today we're looking at the analytical chemistry behind SpaceX Starship. We'll start with the infrared spectroscopy to monitor the combustion of the liquid methane and oxygen. To generate our theoretical spectra, we use the NICT chemistry webbook as a baseline for the pre-combustion mixture. We see a dominant CH stretching peak for methane near 3015 centimeters and a bending mode of 1306 centimeters. Interestingly, oxygen is IR inactive because it's a homonocular diatomic molecule with no dipole change, so it doesn't show up. Once combustion occurs following the stoichiometry of the formula, the methane peaks disappear. They are replaced by the signature doublet of the CO2 at 2,350 centimeters, and the broad jagged forest of water vapor peaks centered around 3,700 centimeters and 16,000 centimeters. This shift allows engineers to confirm complete combustion in real time. Part 2. XPS analysis, the engine residue. Next, we move to X-ray photoelectron spectroscopy to analyze residue on the test stand. To simulate this spectrum, we factored in both the engineering materials and environmental contamination. Because the sample was measured in air, we first plotted the adventitious carbon peak at 284.8 eV. However, since there is an incomplete combustion, we see the broadening of this peak towards higher binding energies representing CO or C equals O bonds from partially oxidized fuel. For the copper cooling components, we plotted a spin orbit doublet. The Cu to be at 932 eV and Cu at 952 eV. Because the test happened in Earth's atmosphere, we added the oxygen 1's peak at 531 eV. Crucially, we included shake-up satellites between the copper peaks. These are the fingerprints of CO, proving the copper oxidized when it hit the air. The mass spectroscopy, methane versus kerosene. Now for the fuels. In the mass spectrometry, we sort molecules by their mass to charge ratio. For the Starship's natural gas fuel, the spectrum is simple. The base peak is the molecular ion of the methane at M/Z16 with fragments at 15 and 14. Kerosene used the Falcon 9. It's much messier. It's a mixture of long-chain hydrocarbons, typically C12 or C15. When we generate this spectrum, we visualize a hump of peaks. You'll see repeating groups separated by 14 AMU, which represents the loss of CH2 units as the long chain fragment. This explains why kerosene is prone to coking or soup. These heavy chains don't always break down into CO2 cleanly. The instrumentation and comparison. To get this data, we use 3 distinct instruments. The FITR uses the interferometer to process all frequencies at once. The mass spec uses a vacuum and magnetic or quadruple analyzer to sort ions, and XPS requires ultra-high vacuum so the ejected electrons don't crash into air molecules before hitting the detector. In conclusion, while kerosene is dense and great for first-stage thrust, methane is the much cleaner choice. Its simple structure, just 1 carbon and 4 hydrogens, allows the suit of free combustion we saw in the IRMS analysis. This makes it ideal for Mars mission, where we need to produce fuel in the situ and refuse engines many times without scrubbing out carbon residue. Thank you so much for watching.